welcome back. Today we're starting our very first lesson of our derivative unit, one of our three major units in calculus: limits, derivatives, and integrals. So we're going to start today with the definition, and the reason why we've been spending all this time talking about limits in the first unit. And so what we have here is something called a derivative. Before we get too bogged down in the notation, let's talk just for a minute about what it is. So essentially, it's a way of finding slopes or rates of change. And so back in algebra, we'd find a slope. We'd take y2 minus y1 divided by x2 minus x1. We're going to be doing the same thing here, except we're dealing with situations where we have something that isn't a straight line. So back in Algebra 1, or first year algebra, we would have a line, and maybe we'd make a little slope triangle, and we'd have our rise and our run. In calculus, it's going to be a little different. Maybe we have something like a parabola, and we want to know the slope, call it the derivative, or the rate of change at that point. And so we're really looking for the slope of the line that goes through that point. And so what we're dealing with today is a little trick for how to find those on something that's a curve rather than a straight line. So for your notes, you're going to want to make sure you have this thing down. The technical name of it, it's called a difference quotient. And then it's also written down here, f with a little apostrophe. The way we say that, we say f prime. Okay, let's look at how to use it. Okay, we'll do our first example here. We're given a function, we're asked for the derivative, difference quotient, derivative, they're coming from the same thing, and we're told that x equals 2. And so all I'm going to do is I'm going to plug in a 2, and I'm going to do exactly what this says. So here's what it looks like. Well, by the way, I didn't mention anything about this. This is dy dx, is how we say it. I know it looks like dy over dx. Normally we say dy dx. And the connection for this is, remember how slope in Algebra 1 was rise over run? And sometimes we would call that delta y over delta x, like the change in y, same thing as the rise. Change in the run, same thing as the change in x. That's exactly what this is. This is where it comes from. It comes from a guy named Leibniz out of Germany in the 1600s. And all he's doing is he's using a d for delta, and he's using a d for delta there. The y and x are the same thing. It's different notation because it's indicating that we're doing a derivative in calculus, that's all. Okay, so here's how it goes. So what I'm going to do is I'm going to start by rewriting this, but I'm going to plug in the information that I have. So it's still going to say limit as h approaches 0, but now it's going to say f of 2 plus h minus f of 2 over h. And then we're going to go ahead and simplify this out. Now remember, when we see this 2 plus h there, what it's saying to do is take the f function, but instead of writing x, every time we see x, we're going to write 2 plus h instead. Here's what it looks like. Limit as h approaches 0 of, okay, so you're going to take the f function, 2x minus 3, but it's 2 times 2 plus h minus 3. I'm going to color code this. Hopefully it stands out on the video. So we're doing that subtraction right there. And then we continue. Now it's f of 2. So again, write the f function, but don't write x. Plug in a 2. So we get 2 times 2 minus 3 over h. Okay? And so what I've got on the board is what a typical calculus student will usually write the first time they try this. And there's a major mistake in this. You may want to pause the video and see if you can find out what the mistake is. It's subtle, but it totally changes everything. Okay? So what it is, it's right here. This has to be in parentheses, because we're subtracting whatever f of 2 is, and so we need to simplify f of 2 first. Or, if you like, understand that we're subtracting it, so we're subtracting a negative 3. If you don't have parentheses, the negative 3 is being added, not subtracted. Okay, so now we can go through and we can start simplifying this. So what I see right away is I have a negative 3 minus a negative 3. Those can go away. And I'm not sure what else yet. So let's simplify a little bit and see what happens. Limit as h approaches 0. Let's distribute. And I get a 4 plus 2h. I have a minus 4 back here. Ooh, that looks good. And so now the 4's can cancel. 4 minus 4 goes away. We're going to continue to simplify. An h on top and an h on bottom. And so now we're finally able to plug in that 0. We couldn't do it previously because that would have caused division by 0. But now we can. You plug in a 0 to 2, well, there's nowhere to put it. So that is just 2. Question asks for the derivative. Same thing as a rate of change. Same thing as a slope. And we've just found it right here. Now that shouldn't be very surprising, because remember, what kind of function is that? It's just a linear function. And linear functions can only have one slope. And since that is in a slope-intercept form, y equals mx plus b, we can see the 2 is in the m spot, and that means the slope will always be 2. So not a very surprising result, not a very interesting result, but we're just getting this down. Okay, let's try another one that'll be a little bit more challenging and hopefully a little bit more interesting. On this one, we're going to look at a quadratic. Okay, and that was like the example I showed visually about 2 or 3 minutes ago. And now we want at x equals 3 to know the slope or the derivative of that thing. And so let's give it a shot. Okay, I've already plugged in the 3's on this one, so that's just this 3 right here getting plugged in, and also right over here. And so now we're going to write out what that actually means. So here it goes. Limit as h approaches 0. Alright, I'm not going to write the f, I'm going to write the f function. So I'm not going to write x squared. It says to plug in 3 plus h. So let's do that. Okay, so that would be 3 plus h quantity squared plus 3 minus, notice it's that minus right there, minus f of 3, and that will be, looks like 3 squared plus 3. Don't forget to put it over h. Okay, we talked about limits. We said always try to plug in that h. Notice why we can't do that. We're going to have an h on the bottom. If you plug in a 0 there, that's division by 0. Okay. Let's do a little bit of simplification and see what happens. So right off the bat, I notice again, I have a plus 3 right here and a minus 3 right there, and so those are gone. Be careful with this, especially coming off summer. A lot of people want to just distribute that square. That's a 2, by the way. A lot of people want to just distribute that. You can't do that. You have to actually take those two binomials and multiply them together. And so I think I'll actually write out what that looks like just so you can follow along a little bit more easily. So limit as h approaches 0 of 3 plus h times 3 plus h. That's what squared means after all. And then we have a minus 3 squared. I'm going to write not minus 9. 3 squared is 9. Put that over h. And so now we can see we need to actually multiply that out. Limit as h approaches 0 of 3 times 3 is 9. See, 3 times h is 3h. 3 times h is another 3h, so that's a 6h. H times h is h squared, and we have a minus 9 there. And so now, and you'll notice as you work on these, there's a pattern. Stuff always cancels out. If you're getting to a place where you've plugged in what you need to into the f function and nothing's canceling out, for now at least there's a mistake. Okay, so double check your work if that's happening. Stuff needs to cancel out. And right here I've got a 9 and a 9 that'll cancel out, and I'm left with this 6h plus h squared, but my h is still on the bottom. So what I notice is I have an h on the top in both of my terms, and that means I can factor it out. It looks like this. Limit as h approaches 0 of, factor out that h, and then see what remains. So it looks like we have a 6 plus h in there. And there's an h in the denominator. And so now we can cancel out those h's. And finally, we are now able to plug in a 0 for h because it doesn't create any domain issues. It's clearly defined. So now we have 6 plus 0 equals 6. Okay, there we go. All of that for a 6. So pause and understand what it means. It means that we have some kind of a parabola. Let me double check what the equation it was, x squared plus 3. We have some sort of a parabola, and it sits like that, and then we count over to an x value of 3, and we go up to that point. The slope, or the rate of change at that point, it has a slope of 6. Like if you did a rise over run type of deal on this, you'd get 6 as the slope. Okay, so we found it for that one point. Now with that information in mind, we're going to go down here and we're going to look at one of the standard calculus problems that's asked in every calculus class across the country every year, and that's known as the tangent line problem. And so we will be asked to write a tangent line at that point to that curve, and I've drawn it in. You can see it in blue. There it is. And we're going to be asked for the equation of that. Now that might look a little bit intimidating at first, but it's actually really, really easy. Check it out. If you know the point-slope equation of a line, which by the way you do need to know, right there, y minus y1 equals m times x minus x1, this gets really, really easy because all we're going to do is we're going to start plugging in numbers into this thing. Here's what it looks like. Y minus, I need a y value. Okay, I don't know the y value yet. I'm going to come back to that. Equals m. That's 6. We just found it. That was the derivative. We just found the slope. So I'm going to make a little note here for you. You could think of that as dy dx now that we're in a calculus class. Okay, that's what that's going to be for the most part. So that'd be 6 times x minus, and then we need an x value. Oh yeah, the problem gave us one. Okay, so we know that's 3. And then if you know an x value and you need a y value, that's all we need. What can you do? Oops. What can you do? Well, we need to plug in our x value. So I'm just going to drop a little 3 right in there. No big deal. That says 3 squared plus 3. That's 9 plus 3. And I think we know that's 12. And that is my y value, or my f of x value. Same thing. And so now I take that 12, I pop that right here, and the standard thing that calculus students do is they start distributing and solving and doing all kinds of stuff. You do not need to do that. This is completely done. This is completely perfect. The AP exam will take this. The IB exam will take this. Your college professor will take this. Mr. Boyden will take this. This is considered a viable form for a line. So it's done. That's all. So far, we've taken a look at these derivatives only at a single point. Normally, it's a lot more interesting if we can write out a function that describes the slopes at every point in the domain of a function. And the deal with that is that could take a long time if you had to do that individually, like plug in a 3, plug in a 4, plug in a 5. It would actually take forever, because we know that in the real numbers, there's an infinite supply of numbers, and that would take us our whole lives. And so what we're going to do now is we're going to do the same thing, but we're not going to know what the x value is. And so we're going to do it in a general form. And this is the standard way that you'll normally be asked to do this. And so we're going to take this one right here. Okay, we're asked for f, remember that's pronounced prime of x, given that this is our function. And so what I'm going to start out with, I'm going to start out just with the definition of a derivative. Limit as h approaches 0, f of x plus h minus f of x over h. Alright, let's go ahead and start plugging this stuff in. So here we go. Now we're going to have limit as h approaches 0, f of x plus h. That's going to look like 2 times x plus h squared minus 3 times x plus h minus f of x, and that's 2x squared minus 3x. Have you caught my mistake yet? I forgot the parentheses. Okay, don't make that mistake. I'm doing it twice on this video because it's such a common mistake, and it becomes really frustrating for students when they can't figure out why they're not getting the right answer. About half the time, that's why. And then we're going to put the little h on the bottom there. Alright, so let's go ahead and simplify this out now. Okay, so I'm going to start doing a little bit of foiling here, a little bit of distribution here, and so I think this is going to get a little bit wider. I'm going to buy myself a little more space on the side. Maybe I'll cut this off like that and we'll write in our answers at the end. Okay, so limit as h approaches 0 of all this junk. Alright, so I'm going to skip a step here. I'm going to do this one in my head, and I'm going to get 2x squared plus 8xh plus 2h squared. Okay, the way I'm doing that is I'm saying that x times h is going to be xh, and x times h is going to be xh, and that makes me realize that that'd be 2xh, and when you double that, that'd be 4. So be careful skipping steps. It can get you in trouble. Alright, we'll keep going. Minus 3x, minus 3h, minus 2x squared, and plus 3x. Alright, I ran out of space. Okay, I'm kind of fudging it a little bit there. Okay, I'm going to fill in the h, but you know what? The good news is we're about to cancel a bunch of this stuff out, so let's do it. Okay, right here I notice I've got a 2x and a minus 2x. That's nice. And what else? Looks like we've got a minus 3x and a plus 3x. Okay, that's nice. And I don't see anything else that can die completely. And so we're going to have to rewrite it and reevaluate. Limit as h approaches 0 of, alright, less stuff to write this time, woohoo, 4xh plus 2h squared minus 3h over h. Alright, nothing cancels out, so now what? Okay, normally, you're going to get into a situation where every single term has the letter h in it. And when it does, just like we did in the previous example, it's time to factor out that h. So let's do that. Oops. And the reason we like to factor it out is because that's going to allow us to cancel out the factored out h with the h in the denominator. And that removes the issue of division by 0. And now we can plug in that 0. And so what I get is I get 4x plus 2 times 0 minus 3. And that simplifies down to 4x minus 3. Okay, what is that? That is our derivative function. We started out with the function f. We ran it through our difference quotient, and now we have f prime of x, or if you prefer, dy dx. Okay, and let's go back up and double check. We were asked to find f prime. That's it right there. 4x minus 3, that is a derivative function. Okay, now let's answer these questions. We're asked for f prime of 3. Rather than having to go through the whole process 3 different times to answer each of these questions, now we have a function called f prime. This is asking about f prime. So we're just going to plug in these x values. It looks like this. 4 times 3 minus 3. Alright, that's 12. 12 minus 3 is 9. Boom, that one's done. Let's plug in a 0. 4 times 0 minus 3, pretty easy. That's negative 3. And a negative 1. 4 times negative 1 minus 3, that's negative 7. See how quick those are? They're a lot easier now if we're asked multiple questions, or if we're asked about the slope at multiple different x values in our function. There they are. Okay, a couple more things before we wrap up today. A little bit on notation. We've talked about dy dx. So dy dx is a derivative, or a slope function, or a rate of change function, something like that. This over here, do notice a difference. The y is missing. This is a command. It's saying you need to take the derivative. It's the same idea as if you have 3 plus 3. The plus sign is a command. It's saying you need to actually add these things together. This is saying, hey, you need to actually run this thing through a difference quotient. And we are going to learn some tricks and some techniques and some shortcuts a little later. For now, this is telling us you need to set up that big old difference quotient. Limit as x approaches 0, and off you go. And so there's an example of it down here. When you see a d dx sitting in front of something like this, what they're telling you is that this little guy right here is f of x, and they're asking you to find f prime of x. Okay, so note that, because sometimes that's the way you'll be prompted. Okay, one more thing. Okay, we're also going to do something called second derivatives. We just did derivatives. Second derivatives, all it means is you're going to do this process twice. Lucky you. Okay, and I'm assuming you can take the answer, plug it back in again, so we're not even going to do an example of it. There are some notes on notation down here. So instead of saying d dx, they say d squared dx squared. That's saying you need to find the second derivative. That is a command saying you need to find the second derivative of f of x, which is the same as this. This is saying, hey, this is the second derivative, which is the exact same thing as f. We don't say prime prime, it's double prime. F double prime of x, those are all the same thing as a second derivative. Alright, this is our intro video for the difference quotient. Next time we'll be back, we'll be talking about the power rule and how Newton came up with that. So until next time, enjoy and I'll see you later.